Hello, everyone. I'm going to start talking today about the regional petrophysics using iMineralysis. My name is Patricia Rodrigues. I'm a petrophysical advisor at Petro Consulting, and welcome to the SPWLA 62nd Annual Conference. So before I start talking about the iMineralysis regional applications, I want to do a quick review of what iMineralysis is. So we start, and even before iMineralysis, let's just have a few phrases about the multimineral analysis in general. So multimineral analysis is an inversion process to estimate simultaneously the volume of minerals and fluids in the reservoir from well logs while honoring the input log data. This technique has been around since the 1980s, so it's very well known to the petrophysicists, and it's available in many commercial software in a module, then all from Schlumberger and Halliburton and Paradigm, etc. So it's a powerful tool in complex lithologies, but rarely used and often misused due to the difficulty of finding appropriate matrix coefficients for the problem. So in the case of iMineralysis, we're focusing on solving that problem, the problem of finding the appropriate matrix coefficients. So iMineralysis introduces a genetic algorithm to search for those matrix coefficients. It allows the estimation of the mineral coefficient in areas where the coefficients are uncertain, and also automates the time-consuming manual trial and error process of estimating the mineral constants. Because of all that, it allows the petrophysicists to explore spatial variations in important parameters such as water resistivity, kerogen maturity, and clay composition. It basically, we can summarize this in an image. What iMineralysis does is that in the multimineral analysis problem where we have a table of constants that has the property of the minerals and fluids, instead of using one value, which then we have to change with trial and error, we use a matrix of limits. And so we use a range of value for each of the properties, and we use a genetic algorithm to search within those limits for the best solution for our problem. So what do I mean by a regional petrophysical project? I'm talking about projects that cover large areas, could be field scale or basin scale, and that we have hundreds or thousands of wells. What is important here is that the interest is in the regional variability in the mineral and fluid composition. So from the multimineral point of view, we want to understand the mineral distribution and the fluid distribution, but it is difficult sometimes because of these varying properties of the mineral constants. So the idea with this type of project is that we're looking to map the mineralogy from thousands of wells. In this case, we show a cross-section of dolomite, quartz, and calcite in more than 90 wells. And we can see the lateral variability of the quartz and calcite content. So the benefit of doing this kind of project is that we can have an improved regional geologic understanding. What are the limitations of using a conventional workflow for this? Well, the matrix coefficients are obtained manually by trial and error. It assumes the same metric coefficient for all wells. So it's assuming that the properties of your minerals or your mixes of minerals don't change across the area, across the field, or across the basin. The error between the model and measure log is rarely used, and it's very time consuming, and usually only a few models get tested, and typically is tested only in the selected wells. So in the case of the optimization using the multimineral analysis, is equivalent to doing thousands of conventional multimineral analysis. So we do genetic optimization to search for the matrix coefficient in each well. It uses, as I mentioned before, a range of coefficients rather than fixed values. It's semi-automatic, and it's fast, and thousands of models get tested. So we have, in the standard forward modeling versus iMineralysis, we have that in the typical standard ELAN multimin or the IP multimineral solver, we get volume of fraction of minerals and fluids and the model logs. While in iMineralysis, we not only get those outputs, but we also get the constituents properties. So we estimate also what are the properties of the minerals. So we start by modeling the iMineralysis around key wells. In the case of regional project, something that is typical from iMineralysis is that we get a very good fit of the raw data. It's really easy to get to a very good mathematical solution. Then we can run optimizations in the remaining wells. We can, since we have good, it's such a quick process, we can actually set up different scenarios and we can run different models and evaluate what is the uncertainty and also the quality of the results in all the area. Another interesting output that is actually in the new release, this part of the new release of iMineralysis, is that we can, besides giving the typical outputs in LAS logs of your minerals, it also outputs a table with a CSV file with the information from the different intervals of interest or the samples that you are modeling. So you get a CSV file that has the name and location. You have the average mineral volumes per interval. But you also have the matrix coefficients for each of your minerals and logs. And additionally, you get the errors. And I'm gonna quickly zoom in here so you can see a little better. I can get magnifier to work. So you can see that what I mean by the matrix coefficients is that we get the density of the kerogen, the density of the clay, the density of the calcite, and that for each of your logs. So you get the endpoints basically of each of your minerals for each of your logs. This kind of output facilitates significantly the moving of the data from petrophysical software to a geologic software, or also a data analysis one. So you can have your Spotfire or even in Excel if you want to look at any of these outputs versus your production data. And after that, we can create regional maps of interest to assess the variability of, for example, the mineral endpoints, the water conductivity, density of kerogen. We can look at the average data misfit. We can use the statistics of the solution. And of course, we can have the typical average volumes and minerals of fluids. So it improves the geologic understanding. It gives you a faster identification of outliers and a faster tuning of our regional modeling. So a few quick examples here with the maps. We can do variation. We can show maps of variations of endpoints, and this is unique to iMineralysis, and I want to emphasize that. It's something that with all other software, you get the volumes of minerals. Here, you also get the matrix coefficient. So we're mapping here an example of the kerogen density, and in this basin, we know that at the center of the basin is the hotter place of the basin, and you can see an increase in the kerogen density, which is an indication of kerogen maturity. We also can look at water conductivity independently. So we have here that we see lower water conductivity to the south. We have to, of course, combine this, for example, with a temperature map to understand if this change in conductivity is due to changes in temperature or there is also a change in salinity in the area. We can explore statistics of multiple realizations because the process allows you to, for example, change the seed of the optimization. You can change the ranges or you can change the log tolerances and rerun the models. And you can look at in this case, we're looking at the variance of the volume of calcite. We can see some of the points the variance is really low, which means that whatever our volumetric estimation is very consistent. And you have other points where you have a higher variance, in which you can see that it's not as stable. The results mean that we have more variability. We also can map the misfit for all the curves, and we can start looking at trends that it's kind of like a nice QC step. It not only tells you that maybe the model is not working well there, it's also when it's so systematic, we can tell us that there is something geologic going on to that region. And it may need either a different multimodal model or actually a different normalization when we did the process. And As the typical multi-analysis, you can map the volume of kerogen, of course, and the volume of calcite, like a typical multimineral output. So the summary of this, the advantages of the regional iMineralysis is that it's much faster. It adjusts fractions and matrix coefficients simultaneously. It allows areally varying matrices of coefficients. Basically, we have an optimal data fitting for each well. And we can then do regional mapping of coefficients, which give us also insight into geology. See, if you see changes in kerogen density or changes in the properties of the clays, you can start thinking about clay changes in the area. It minimizes modeling errors and reduces uncertainty, and also reduces user intervention. So we have a better understanding of the target, and we can make better decisions.